So let us continue from what we were discussing yesterday. So we have started discussing threads, and we have understood that modern OSL, in modern operating systems, there is a concept of a multi-threaded process. So a process, as we have been discussing till last week, has a single thread of control, but a process can be multi-threaded, and each thread will be a different uh, thread of control. And we have discussed some real life use cases, like in a browser, let's say, maybe you are downloading one large file, and simultaneously you are checking mail. So the browser will possibly use a multi-threaded approach so that both can continue. Similarly, we talked about a network server. So a server, typically say an email server kind of, so that server will possibly use many threads, and each thread will be used to service one client. So ideally, when we have a server, we expect many clients to connect to it. So one popular design principle is have one thread to talk to or to service every client. And the parent thread, the one which had started the first, that creates these, so that listens for new connections. Once a new connection comes, it creates a new thread, and then the threads run concurrently and so on. Okay. And we also discussed two strategies for using threads: asynchronous threading and synchronous threading. Right? So asynchronous threading is like this server example that I said. The parent thread and the child threads, they execute concurrently and they are independent of each other. So the parent does not need to know when the child threads terminate and so on. The threads are not sharing much data. However, in synchronous threading, the situation is like there is a large data structure and different threads are doing some computation over different parts of that data structure. So the parent thread needs to know when the child threads complete so that it can assimilate the results and give out a final result or something like that. And we have also discussed that what is the benefit of these threads. Main benefit is twofold. One is threads are context switch between threads is much lightweight than context switch between processes. Right, so context switch between processes require a lot of overhead, saving a lot of information and so on. But context switch between multiple threads of the same process is much lightweight. This is because threads share a lot of data, like the data segment, the code segment, these are all shared among all threads of a process. And herein comes the second advantage of threads. Communication between two threads of the same process is much faster or more efficient than inter-process communication. Because inter-process communication typically requires kernel support. So you write to a pipe, or you access a shared memory. These things we have discussed, right? But when you access a shared memory or when you write to a pipe, kernel support is needed. So effectively a context switch is needed. But since multiple threads of the same process have the data segment common, they can simply talk to each other using variables even. Like one thread puts the value in one variable, another thread simply reads that variable. These things can happen. Okay. Now we discussed that we will be talking about a particular thread library. So there are several popular thread libraries. There is one for Linux or Unix based systems called pthreads. Then Windows has a thread library, Windows threads. Java has its own thread library and so on. So using these libraries, it's easier for programmers to write multi-threaded programs or multi-threaded applications. Out of these popular thread libraries, we will study pthreads, the one which is used by Linux or Unix systems. So first of all, what is POSIX? POSIX, the full form is this: it's a portable operating system interface. Okay. It's basically a family of standards for maintaining OS compatibility. So there are many versions of Linux or Unix. I think you know, many flavors, many versions. Using such standards like the POSIX standard makes sure that if you write a program meant for one flavor of Unix or Linux, it should run in another flavor of Linux too. Because the thread libraries given by both these versions or flavors of Linux will follow the same POSIX standard. Okay, so that is why specifications or standards are used, and you see them everywhere in systems. Like in the networks course, I'm sure you are going over many standards, right? So, and that is because maybe you have created your web page in one particular machine, but when someone else sitting at another machine also accesses that web page, they should see the same thing, right? So that is why there are lots of standards like TCP, IP. So there are protocols or standards. So similarly, POSIX is a standard which is meant to enhance portability between different operating systems. So different versions of Linux, etc. So the POSIX standard basically tells the OS what function calls need to be supported. It's basically an API. It defines an API. So this part is important. What we are going to study is actually an API for thread creation and synchronization. Okay. POSIX does not say exactly how to implement this API. That is the work of the person who is designing the library. For you, as the programmer, the job becomes simple because you have an API. So you exactly know what functions you can call. Okay. So that is the role of POSIX. Okay, now we discussed this point a bit yesterday, that a thread library can be user level or kernel level. So what does that mean? That see, every library has its own data structures. At what level are those data structures? So the user level, if a library is user level, that means the data structures of the library are in the user space. But if it is a kernel level library, then the data structures, etc. of the library are in kernel space. And like for you as a programmer, the difference would come that in case of a user level library, if you make a library function call, then it will be at the user level. But if it is a kernel level library, then a function call, a library function call will actually lead to a system call. So again, POSIX does not say whether to give the implementation as a user level or a kernel level. That is left to the designer. POSIX simply says, or POSIX pthreads simply says, these functions should be implemented for thread creation and synchronization. Now it is up to the designer of the an actual implementer of the standard to decide whether the implementation would be at user level or at kernel level. Fine. So POSIX is quite popular, and all major thread libraries in Unix or Linux are POSIX compatible. So let us see, let us understand this POSIX pthreads library a bit more. Typically, this is what you have to do. You have to include this header file pthread.h in the main source file, and you have to compile the program with this flag. So -l pthread. I think you understand this is, we are telling the GCC compiler to link the pthread library. Right. So I think I don't need to explain this part. You have done a compiler course and so on. Now, according to this standard, there is an important distinction between global data and local data. Any variable or data which is declared globally are shared among all threads of the same process. But local data, that means data which is declared within a function, That we know from, I mean, all of us know from our knowledge of, say, compilers or Goa, that data local to a function are stored in the stack. Right? So when a function call is invoked, when a function is invoked, the local variables of that function get created on the stack. Now remember what we discussed yesterday, that threads have their own stack. So multiple threads of the same process, they share the code segment, data segment, etc. But the stack is separate for every thread. So there are some entities which are separate for every thread, like the stack, the program counter, the register variables, and so on. Right? So since each thread has its own stack, and since data local to a function are created on the stack, then each thread has its own copy of the local data. Okay. So the global data is shared among all threads. If you actually want to have one variable shared among all your threads, then declare it globally. And if you declare data within a function, then that would be local to individual threads. And also, according to this API, when you create a thread, we will soon see how, but when you create a thread, you have to specify a function, and your threads will begin execution in that specified function. The situation is similar to how the parent thread runs. So it's well defined that actually, at least in a C program, the first thread or the parent thread will start in the main function. Similarly, when you create other threads, you have to specify a function with which the control of that thread will start. Okay, so the thread will start executing with that function which you specify. Okay, now let us actually see some code and understand how to use pthreads library. For that, we will use a simple example. We assume that there is we are writing a program where a number n will be taken as input, and then a separate thread is created which will calculate the sum of first n natural numbers. Right? So it will create a thread which will calculate the sum of n natural numbers. And n is an input, and we will follow the synchronous mode of threading. That means parent thread will wait for the child threads to end. So this is just our choice. As in, we could have done things asynchronously, but we want to adopt the synchronous mode of threads. There are actually some problems with the asynchronous mode of threading. We will discuss that very briefly, like later today or tomorrow. Okay, at that point, so now we will actually see the code. Any questions at this point? Okay, if not, let me proceed with the code actually. So as in earlier classes, I'll point out the system calls, etc. But we won't go into too much details of individual system calls. Like I won't attempt to describe every parameter, etc. That is your job to figure out. And so go through the man pages, etc. or go through other resources, and we expect you to figure out the details of the system calls that we discuss. Okay, so the code, in that code, as I said, you have to include pthread.h. And here we are declaring a global variable, sum. And so we want this sum to be shared over all threads. And we are declaring a function here, runner. So as I just said in the previous slide, while creating a thread, you'll have to specify a function where the thread will begin executing. So this runner is that function. Okay. See, the convention is to declare it as a void pointer. So it returns also void pointer, and it takes as argument also a void pointer. So okay, just I'm sure all of you know this still. What's the idea of void pointer? Why do you think this runner is, so what's the idea of declaring, say, its argument as a void pointer? Yeah, so yeah, as expected, most of you understand that, yeah, I mean, we want to keep a mechanism of being able to pass different types of data types to this function. So we can pass, say, an integer pointer or float pointer, and a void pointer will be able to like point to all these. The issue is that we have to typecast, so that we can do later. So this is a common convention used in generic functions where we are not completely sure maybe from the beginning that what data type we want to pass it to, or we want this, or we want this function to be a bit more flexible. Okay, let's go ahead. Now we will have two functions in this program, as you understand, the main and the runner. So main is that function where the parent thread will start executing, this we all know, and runner is that function where every thread that we create will start executing. Now these are some of the things that we need to do in order to create a thread. So we first need an identifier for the thread that we will create, and that identifier is of type pthread_t. So as you understand, these data types are defined in pthread.h. Okay. So we have this thread ID, it's an identifier for the thread that we will create, and we have a structure of this type, pthread_attrt. This structure will be used to store attributes of the thread. Now, there are different types of attributes that a thread needs to store, one of which is the stack size. And again, look, if you're interested, look at the man page, etc. to understand, or look up some internet resources to understand what are the contents of that structure. I'm not going into those details here. And then you call this function pthread_attr_init, and you pass it to it the address of this structure. The idea here is that you want to create a thread with default attributes. Okay. If you did not, or if you wanted to change the attributes, that means if you want to have some specialized attributes and not the default attributes, then you will need to pass some other flags to this function. Again, I'm not going into those details, but look this up. So here we are just creating a thread with default attributes. If you specifically want to have a thread with some specialized attributes, you need to pass some flags to this function. Okay. Now, actually we are creating the thread. So creating the thread is done by this function called pthread_create. And you can see what the parameters it takes. It takes this pointer to this thread ID, a pointer to this attribute structure, this function where the thread should run. So what is this actually? What is this runner? So what is it? It is an integer, it's a pointer, what is it? Yeah, it's a function pointer. Right? So again, I hope that the concept of function pointer is known to you. So it's a function pointer. Okay. And then this argv1, this is what we have decided, that the program will take as one command line argument the value of n, and the program will sum up the natural numbers 1, 2, 3 up to n. So this is that mean, the argv1 is that command line argument. So basically, okay, okay. So basically, this argv1 would be sent to a runner as argument, right? This would be sent to runner as argument. That is how this pthread create will work. It will create a new thread which will start working in this function runner, and this will be sent to runner as an argument. Okay. So at this point, suppose when this function call is done, then the new thread has been created, and the new thread will be running with this function. I mean, will be running in this function. So what do we want the main thread to do in this program, or in this example? We want the main thread or the parent thread to wait for the child thread to complete. Hence, we call this function pthread join. Okay. So we are calling this function because we want the parent thread to wait for the child to terminate. Again, look at the details of the parameters. But yeah, of course, one parameter is intuitive. We have to tell this pthread join which thread this parent is waiting for. Okay. So here specifically the parent says that I am waiting for this thread to complete. Okay. So after that, so the way we write the program is this, that pthread join will do its job and will update the answer, that means the sum of the variables, in this global variable sum. Remember, this is a global variable, therefore this is shared among all the threads. So both the parent thread running in main and the child thread running inside runner can access sum. That is the motivation of declaring this as global. So main will just print out that sum. Now let us see what runner does. So this is the function which the thread will run. So let us see what runner does. Okay, first this n is taken as a 2i param. I mean, very much ideally you should have typecasted this to char pointer, but I think it's okay. So basically n takes the value of, I mean, that natural number till which we have to sum, and then it's simple. It's very simple. You just add the numbers till sum. And the last statement is this, pthread exit. So pthread exit, by calling this function, the thread terminates and it sends back a status value of 0. Again, we have discussed this at some point earlier, that usually the convention is that if everything has worked properly, then we return, I mean, then a process returns with, then a function returns with the return value 0. That's just a convention, right? That if everything has worked fine, then your function returns with 0. And that's why you write return 0 at the end of main. So here also this thread wants to send back the status 0, and this is the function to do it, pthread exit. So if a thread calls pthread exit, then that thread will terminate and the status will be sent back to the parent thread. This is very similar to how we discussed during processes. Like a process can also terminate and send back a status to its parent process. Here also. Note one thing, pthread exit, this function is different from exit. The exit thing which we have used earlier. What do you think is the main difference between pthread exit and exit? I mean, it's intuitive from the name, but yeah, what do you think is the difference between pthread exit and exit? Yeah, Shubham has the right answer. So exit means you want to end the whole process, including all threads which are running in that process. But here we don't want that. We want to end a particular thread. So for that, the function which is provided by this pthreads library is pthread exit. If by mistake you call exit here, then all threads of that process and the entire process will terminate. The pthread exit is only for terminating this particular thread which has called it. Okay. Remember, I mean, in this very simple program, we created just one thread. It's quite possible that we create multiple threads and all of them are running in this program runner, I mean this function runner. Then that thread which computes, that thread which calls pthread exit, only that thread will terminate, not the other threads. Okay. Okay, time for some questions. I see already one question from Tanmay. If we wait for child to run, then isn't this becoming similar to process? They are not running simultaneously. Okay. 2 points here. First of all, we discussed this in detail yesterday, that actually threads are not running simultaneously. They are still running concurrently, because we have assumed in this course that we have a uniprocessor system. So if you have one processor, then only one thread can run at a time. So the word simultaneously I especially am objecting to, because it seems to, I mean, it can be confusing. That are the different threads actually running simultaneously? The answer is no. We have one processor, therefore threads are running concurrently. Okay, but I do get Tanmay's question. So the thing is whether the parent waits for the child. Okay, first of all, it's completely your decision. I mean, there is no question of having to wait for the child. As I said, there are many programs which do not wait for the child. A typical example is a network server. Server just creates threads. Each thread handles a different client request, and the server is not waiting for the child. The server keeps on listening at its socket or port for new requests. Right. So whether the parent is waiting for the child is completely your decision. And it was the same in case of processes also. Whether your parent process waits for your child process, that's your decision. Similarly, whether a parent thread waits for the child thread, it's also your decision. So if you do not give this pthread join call in main, then your parent thread will not wait for your child thread. Your parent thread will execute independently of your child. So both will be in the, let's say, ready queue, as well when one is scheduled, it will run. Okay. So, okay, does that answer Tanmay your question, or if not, unmute yourself and say. Okay, good. So any other question about this program, etc. Please don't ask for the details of these function calls. Neither do I remember them, nor do I mean to cover them in this class. This is for you to figure out, like what the specific functions are, I mean what the specific arguments are. But apart from that, any other question about this program? Okay, that's a good question. From Rashil, why are we resetting sum in each thread? Isn't sum a global variable? Yes. Again, This is meant to be a very simple program where we know that we will create just one thread. That is why sum is initiated here. If you actually have a more complicated example, let's say you have a large array and you are creating 5 different threads to sum up different parts of the array, then definitely each thread will not initialize sum to 0. So then maybe you would work like each thread has a local variable which it computes, and there will be different global variables. Each thread will update one of them, and then the parent thread will sum up all those variables and give the final sum. So this is a good question, but this is just because this is a very simple example where we knew that we are going to create just one thread. Okay, let me proceed. So the next example that we will see is actually an example of the same type, but we will just demonstrate how to create multiple threads. So before going there, let me ask you, what changes do you think we will make to this program? Suppose we want to create some number, like say k threads. What changes do you think we will make in this program? I'm asking because the changes are very intuitive. So I believe some of you will be able to guess it already. What do you think? What changes do you think we will make to this program if we want to create k threads? Good, create and join in a loop. But what about the data structures here? Like TID, ATTR, what about those? What do you think? How do you think we will change them? Exactly, as simple as that. We will have then arrays. So now we have only one thread ID. Now we have an array of thread IDs. Okay. So basically, yeah, as I said, some of you have already guessed what changes we will make. Let us actually see the example that yes, that's the case. So in this example, we are creating many threads. So first of all, we hash define this thing nthr, number of threads, as 10, say. Now first change is this. Instead of having only one TID, now we have an array of thread IDs. Okay, we have an array of thread IDs. And we are creating threads in a loop. So we are creating these many threads. Again, see, every time we are passing to it one thread ID, the address of my threads I, and we are reusing this ATTR. Okay, we are using this ATTR. Why do you think we are reusing this ATTR? I mean, why didn't we have an array for ATTR also? Why did we not have an array for ATTR also? I mean, this question, like what do you think is the purpose of ATTR? Let me go back to this. Yeah, let me go back to the previous program. So this was ATTR, right? So I'm asking why don't we need an array of ATTRs also? Yeah, specifically what like Mukul and Ramnivas have said, or Shubham also. In this program, we are just assuming we are creating all threads with the same default attribute. Therefore, we just filled it up. See, in this call here, we filled up ATTR with the default attributes. And since we are creating all threads with this default attribute, only one ATTR is sufficient. Of course, if in a more complicated example, you would have wanted to create different threads with different attributes, then you would have to have different such pthread ATTRT and then adjust different attributes according to what you want. But here in this simple example, we are assuming that yes, we are creating 10 threads now, but all of them will have the same default attribute. Therefore, we don't need an array of ATTRs. However, we need an array of thread IDs because we need somehow to differentiate between all the 10 threads. Okay. So as some of you guessed, we are now creating arrays in a, sorry, we are creating threads in a loop. And similarly, the join statements, they will also have to be in a loop, because again, we want to write this program such that the parent thread waits for all child threads to complete. You may or may not take this design, that's up to you. But then if we suppose we want that, then this is what we have to do. The pthread join, it will wait for all threads to complete. So basically we call this pthread join 10 times, every time giving it a TID, a thread ID of one particular thread. Right, so this parent thread will start running or will resume running only after all child threads have ended. Fine. Any questions? Yes, we are following synchronous thread design mechanism. That means the the parent is waiting for the child threads to complete. I'm pretty sure that in your networks course, you will be creating asynchronous threads, but I don't know if you will be asked to do that with threads or processes. But yeah, I guess that in your network course, you will design a network server where you will see the asynchronous mode also. Any other question? Okay, now let me proceed. So this is a point which I had asked you earlier. Some of you had guessed. So there's a difference between exit and pthread exit. So exit kills all threads, including the main thread. But pthread exit only kills that thread which has called this function. But the process and other threads are kept alive. So this is the difference between exit and pthread exit. And finally, we discussed about this data type, pthread attrt. This is basically a thread attribute, right? And the attributes define the state of the new thread. A state may contain many different things, like the system scope, something called whether it is joinable, the stack size, etc., etc. So you can basically you can create, as I said, you can create threads with default attributes. Then the system will assign some values. Or if you want, you can actually set particular attributes of a thread. And for that, these functions are given. Pthread attr set attribute or pthread attr get attribute. So if you want to change some default settings in some threads, then you can use these functions, pthread attr set attribute. Okay, so again, I'm not going into details of how to set attributes, etc. I leave that as a task for you to figure out. Okay. Okay, any questions? Okay, if not, let me go to, so this slide deck ends, but let me go to the next slide deck, where we will continue discussing threads. Okay. Now, are these slides visible? Just to confirm. Okay. So yeah, so till now we have discussed these things like what is the thread, why do we need that, and we have also discussed the POSIX pthread library. Okay. Now let us talk a bit about thread scheduling. I mean, there was a question yesterday also. We have not answered that fully yet. This is the point where we will answer it. But how are these threads scheduled? So typically, we have discussed that there are two types of threads broadly: user level threads and kernel level threads. And we discussed different ways of mapping user level threads to kernel level threads. Like we discussed one-to-one mapping, many-to-one mapping, many-to-many mapping. So one question is, how are these threads scheduled? And for that, there are two scheduling paradigms: process contention scope and system contention scope. Right? So just from seeing the names, what do you think they would do? What is contention scope? What do you think? So this part is common, right? Contention scope. What do you think is contention scope? Yeah, okay. So what Shomnath has said is maybe closest to what it is. So basically contention scope, so what the word contention indicates that the threads are contending or competing for something. And probably they are competing for the CPU. Right. So the question is, what is the scope of this contention? So let's now see these and it will be clear. So in process contention scope, the thread library schedules the user level threads to run within the assigned time quantum for the process. So basically, all the threads of the same process are contending for the CPU, or you might say contending for CPU time. So a particular time quantum is assigned to the process. This is what we have discussed earlier. Within the time quantum, now some subpart will be given to one thread, some subpart will be given to another thread. So essentially competition for CPU takes place among threads belonging to the same process. That's why process contention scope. So the threads within the same process are contending for CPU time. It's also called unbound threads. In contrast, the system contention scope, I think most of you have guessed it. Competition for CPU takes place among all threads. Sorry, it's written wrongly here. Competition for CPU takes place among all threads in the whole system. I'll change this one. Right, so the system contention scope. So competition for CPU takes place among all threads in the system. Right, it's also called bound threads. So the pthread library defines these two contention scopes: pthread scope process and pthread scope system. And as we just discussed 5 minutes back, oh sorry, these are not the attributes, but yeah. So pthread again defines these two functions to actually set the scope or know the scope of a process. So this is again the scope is contained in the thread attributes. So pthread attrt, that is, we discussed this. This is where many attributes of the thread are stored. One of these attributes is the scope. Right, so pthread attr set scope, you can use it to set the scope, and get scope you can use it to know or get the scope. So these two are the scopes, the process scope and the system scope. However, in the most Linux systems, the pthread scope system is supported, but not pthread scope process. What does that mean? That means essentially Linux, at least in this context of scheduling, does not differentiate between processes and threads. All threads that are there in the system. So maybe there are many processes running, some processes are single threaded, some processes are multi-threaded, etc. Linux considers all of them as tasks or threads and then decides scheduling among all of them. Okay. So maybe some other operating system can also implement the process scope, but at least Linux does not. Okay. So, I remember that this question was asked yesterday. So now you see that, so it's possible to have both mechanisms. One is that the system scope process, the process contention scope, where all threads within the same process are competing. That means the particular, a time quantum is given to a particular process, and that is being shared or divided among all the threads in that process. And in the second case, like all processes of the system, all threads in the system are contending for the CPU time. Okay, yes, so yeah, the question what Mukul is asking, yeah, if a particular operating system implements pthread scope process, then I would imagine that the scheduler will only schedule processes, and then in that time quantum which is allocated to that process, that will be somehow shared between the threads of that process. Right? But Linux does not support that. Linux considers all threads across the whole system and then schedules. Okay. Okay. Fine. Just 1 minute. Yeah. So let's just discuss one small thing today and then I'll end the class. So we have discussed about thread creation. We have discussed about process creation. We have understood the fork, call, and so on. But now we are talking about multi-threaded processes. So do you see any issue about how should fork behave in a multi-threaded process? Do you see any issue here? So we know how fork works, it replicates the process. But now this week we talked about multi-threaded processes. So does any question come to you now related to fork? Exactly. What the question which Sriharsh asked, or Shubham also asked, that suppose a multi-threaded process and one thread calls fork, then what should be done? So this is the question. Say if one thread in a process calls fork, does the new process duplicate all threads in the original process? Or is the new process single-threaded? That means only that thread which has called fork should be in this new process. Right? I hope the question is clear. It's a multi-threaded process and one thread has called fork. Then whether the whole process should be replicated or only that thread which has called fork, that thread as if should the new process have only that thread which has called fork? Now again, this is a design decision, and several operating systems have done it either way. As in some Unix systems or Linux systems have two different system calls or two versions of fork. One which duplicates all threads and the other which duplicates only that thread that invoked fork. Okay, so both are possible. About exec, there is not much confusion. So that semantics is kind of clear. That if any thread in a process calls exec, then the whole process will be replaced by that program which was specified in exec. Right, so I mean the exec semantics has been made clear, like even if one thread crawls exec, the whole process will be replaced by that program which was indicated in exec. Right. Okay, and yeah, so last slide for today. Specifically for Unix, it actually provides two different system calls. The fork system call to create a new process and the clone system call to create a new thread. So when you call the pthread library function, pthread create, etc., underlying that library will call the clone system call. Okay. So, and basically a set of parameters is passed to clone to indicate how much sharing is to take place between parent and child thread, etc. So we are not going into details here, but just to, I just wanted to point out that this question exists, that if a thread calls fork, what should be done? Whether the whole process should be replicated or only that thread. So basically the Linux has chosen it this way, that fork and clone, there are two separate system calls given. Okay. So I want you to carry out this experiment that suppose you have a process with multiple threads and one thread calls fork, then what happens? The new thread, the new process that is created, how many threads does that have? Right, so think about an experiment or a small code that you can write to check this and maybe check this out. Okay. Fine, we end this class today, it's a bit late. We will continue tomorrow we have some other things to discuss about threads. We will continue it tomorrow. Okay. Thanks everyone.